In this tutorial, we will learn how to create an instrument parameter file from a lanthanum hexaboride or LaB6, a reference XRD pattern using GSAS-II. The goal is to build a practical understanding of how a reference material is used to describe the peak shape behavior of an X-ray diffractometer. By the end of the session, we will have a clear workflow for preparing the LaB6 pattern, fitting the relevant peak profile parameters, saving the result as an instrument parameter file, and validating whether that file works correctly in a fresh GSAS-II project. In this presentation, we are not treating LaB6 as an unknown sample. Instead, we are using it as a known reference material. Because LaB6 has well-defined diffraction behavior, it allows us to estimate the contribution of the XRD instrument to the measured peak shape. The key idea is that every measured peak contains both sample contribution and instrument contribution. Our task is to separate these two as carefully as possible, then save the instrument-related part as a GSAS-II instrument file. This file can later be reused for samples measured under the same instrument configuration. LaB6 is widely used because it is an excellent reference material for instrument profile work. A good standard should have known peak positions, sharp diffraction peaks, very low intrinsic broadening, and reflections distributed over a useful angular range. LaB6 satisfies these requirements very well. Its simple cubic structure gives a clean diffraction pattern, and its low sample broadening helps us see the instrument contribution more clearly. This is why LaB6 is especially useful for line position and line shape calibration, and why it is preferred when the purpose is to build an instrument profile. LaB6 is not the only standard used in powder diffraction. Different reference materials answer different calibration questions. Silicon is very useful for checking peak positions, zero shift, and wavelength accuracy. Cerium oxide can be used as a stable calibration and performance check standard. Alumina is commonly used as an internal standard, especially in quantitative phase analysis. Quartz and other crystalline material can also be used for routine checks. However, for this tutorial, our main goal is instrument peak profile calibration. For that specific purpose, LaB6 is normally the stronger choice because it provides both accurate positions and useful line shape information. Before we start refining, we must define what should and should not be stored in the instrument parameter file. The file should contain information that belongs to the instrument configuration, such as wavelength, profile behavior, and instrument-related peak shape parameters. It shouldn't contain sample-specific effects from one particular LaB6 mount. For example, sample displacement, crystallite size, microstrain, impurity peaks, or artifacts should not be saved as if they were instrument properties. The central principle is simple. We want to save the instrument response, not the history or imperfections of one reference specimen. The refinement must be done in a controlled order. We refine the background because the baseline affects peak intensity and width. Then we refine peak intensities or area first because they are the most stable parameters. After that, we refine peak positions to align the calculated peaks with the observed peak centers. Individual peak widths may be refined only as a diagnostic step to identify abnormal peaks or outliers. The main instrument profile terms are U, V, and W, which describes the Gaussian broadening trend. X and Y should be treated cautiously because they can absorb sample-related Lorentzian broadening such as crystallite size or microstrain. The goal is not to refine everything. The goal is to refine only what helps describe the instrument. The first stage is preparation. In GSAS-II, we start by creating a new project and importing the LaB6 XRD data. Then we set the useful 2 theta limits. This means keeping the clean and reliable diffraction region while excluding noisy tails, artifacts, or regions that do not contain useful information. Next, we fit the background carefully. A practical starting point is 6 to 8 background coefficients. For a clean laboratory pattern, 6 terms may be enough. If the pattern is wider or the low angle background is curved, 8 or more terms may be required. The background should describe the baseline, not the break peaks. After preparation, we build the peak list and refine the peak model step by step. We add only reliable LaB6 peaks and avoid impurity peaks, weak peaks, distorted peaks, and strongly overlapped peaks. First, we refine only peak intensities. Next, we define peak positions. Then, if needed, we temporarily refine individual widths to diagnose outliers. After this diagnostic check, individual width refinement should be turned off. We then refine the global instrument profile terms, mainly U, V, and W. For a short-range pattern, about 8 reliable peaks may be enough for a demonstration. For a wider and strong calibration, 15 to 25 well-separated peaks over a broad angular range are better. Once the peak profile is satisfactory, we save the instrument parameter file. Before saving, we review the refined U, V, and W values and decide carefully what to do with X and Y. If we want a conservative instrument-only file, X and Y should normally be reset to 0 unless we have a clear justification for saving them. Then from the instrument parameters section, we save the profile using a descriptive file name, but saving it is not the final proof. We must validate the file in a fresh GSAS-II project by re-importing the LaB6 pattern, loading the new instrument file, adding the LaB6 phase, and checking whether the file works without immediately changing U, V, and W again. A good instrument parameter file must be transferable. It should work not only in the original project where it was created, but also in a fresh GSAS-II project. During validation, the peak position should align after reasonable zero or sample displacement corrections. The calculated peak widths should match the observed widths across the low, middle, and high angle regions. The difference curve should be balanced without repeated systematic peak shape errors. Finally, U, V, and W should not need large changes during validation. If these checks are satisfied, the file is working as an instrument calibration product rather than just a fit to one LaB6 pattern. Let's begin with the 2 files required for this demonstration. The first is the measured LaB6 powder X-ray diffraction dataset, which we will use to determine the instrument profile. The second is the LaB6 crystallographic information file or CIF, which will be used later when we validate the instrument parameter file. We will start with the raw diffraction data. The CIF is not needed during the initial peak fitting stage. It becomes important only when we test the saved profile in a new project. I will now open GSAS-II and arrange the windows so that the data folder and the GSAS-II interface remain visible. From the menu, I select Import, then Powder Data, and choose the option that allows GSAS-II to identify the file format. I select the LaB6 raw dataset and confirm the prompt to open the binary powder diffraction file. GSAS-II now asks for an instrument parameter file. Since the purpose of this tutorial is to create that file, we don't need yet have a calibrated profile to load. Instead, I select a reasonable generic starting configuration that matches the measurements. In this case, constant wavelength laboratory XRD with copper K alpha radiation. These values are only initial estimates and will be refined from the LaB6 data. The imported skein extends approximately from 10 to 70 degrees in 2 theta. However, the first useful LaB6 reflection begins close to 20 degrees, while the lower angle region does not provide useful calibration information for this dataset. I therefore open the limits panel and set the refinement range from about 20 to 70 degrees. This excludes the unnecessary low angle portion and prevents it from influencing the background and profile fit. It is also important to state the limitation clearly. An instrument profile calibrated only to 70 degrees should be used confidently only within a similar angular range. If future samples are measured to substantially higher angles, the LaB6 standard should also be collected over that wider range. Next, I open the background panel. The Chebyshev polynomial background function is selected and the refine option is enabled. The visible baseline is only gently curved over the selected range, so a highly flexible background is not required. I will start with 6 coefficients. For a very clean laboratory pattern, 5 or 6 coefficients may be sufficient. A wider skein or a pattern with stronger low angle curvature may require 8 or more. Increasing the number of coefficients does not fit the background by itself. It only increases the flexibility of the model. The coefficients are actually optimized when we run peak fitting and choose peak fit. The final background should follow the baseline smoothly without absorbing peak tails or chasing random noise. Before generating the peak list, I verify the main experimental settings. In instrument parameters, the source type is copper K alpha, consistent with the measurement. At this stage, I leave the remaining starting values unchanged. In sample parameters, the diffractometer type is set to break lanthanum and the histogram scale factor is active. These are suitable starting settings for the present laboratory skein. The detailed instrument broadening will be determined from the peak fitting procedure rather than assumed from these defaults. I now open the peak list and generate an initial set of peak positions using the automatic peak search function. Auto search is useful for locating candidate peaks, but the result must always be inspected manually. I zoom into the pattern and check each marker. A valid calibration list should contain one representative entry for each reliable LaB6 reflection. Duplicate markers, weak noise features, distorted peaks, and overlapping features should not be treated as independent calibration peaks. Where the automatic search has placed 2 markers on one reflection, I select delete peaks and remove the unwanted entry. I repeat this inspection across the entire pattern until the list contains only clean, trustworthy peaks distributed from low to high angle. The first refinement is deliberately simple. I enable refinement for the peak intensities or areas while keeping the peak positions and widths fixed. This is the most stable place to begin because it allows the calculated peak heights to approach the observed data without changing geometry or profile shape. I choose peak fitting and then peak fit. GSAS-II asks me to save the project, so I save it with a descriptive name such as LaB6 reference. After the first cycle, I inspect the calculated intensities. If necessary, I run peak fit once more so that the intensity parameters fully converge before introducing additional variables. Once the peak intensities are stable, I enable refinement of all peak positions. I double-click the position refinement heading and select Vary All. While retaining the intensity refinement, I then run peak fit again. The peak centers may move slightly because the initial markers were placed manually or by automatic search, and because real peaks can be mildly asymmetric. The purpose of this step is to align the fitted peak centers with the observed maxima. At this stage, I am still not refining the global instrument width parameters. We can now examine the individual peak widths. In GSAS-II, sigma squared represents the Gaussian variance contribution, while gamma represents the Lorentzian contribution. I first enable sigma squared refinement for the selected peaks and run peak fit. If a starting intensity is extremely poor, it can be adjusted manually before rerunning the least square fit, but the final value should be determined by peak fit. I then enable gamma and repeat the fit. This is a diagnostic stage. It allows each peak to determine its own width so that we can identify outliers and understand how the profile changes across the angular range. The next step is the core of the calibration. Individual sigma squared and gamma refinements are now switched off because we no longer want every peak to have an independent width. Instead, we want a single smooth instrument function that describes the width trend across the full pattern. I inspect several low, middle, and high angle reflections and confirm that the fitted peak shapes follow the observed profiles. I also inspect the difference curve because a visually acceptable peak height alone does not guarantee a satisfactory profile. At this point, I return briefly to the background panel and confirm that the baseline is being described smoothly. For this dataset, 6 coefficients provide a reasonable background without unnecessary oscillation. I then inspect the fitted peaks one by one. The background between reflections should be stable and the residual should not show broad systematic curvature. Any strong positive and negative feature around a peak indicates that the peak position, width, asymmetry, or profile mixture still needs attention. This inspection tells us whether the individual peak fits are reliable enough to determine a global instrument function. In instrument parameters, I enable U, V, and W. These parameters define the Gaussian width contribution as a function of diffraction angle. I initially keep X and Y fixed because these Lorentzian terms can also absorb broadening associated with the LaB6 specimen. I return to peak list and run peak fit. During this fit, the position and intensities remain adjustable while the widths are generated by the global U, V, and W relationships. I then inspect both the powder pattern residual and the peak widths plot. A successful model should produce a smooth fitted curve that follows the width points obtained from the individual peak analysis. If the global profile fit is not yet satisfactory, I perform a control iteration. I verify that the peak positions and intensities are still enabled. I run peak fit again and compare the new residual with the previous result. I do not refine individual Gaussian widths at the same time as U, V, and W because those parameter sets compete to describe the same feature. If the low-angle peaks show a clear asymmetric mismatch, I can test the SH over L asymmetry parameter. I enable it briefly and rerun peak fit. If the value does not change significantly or if the residual doesn't improve, I disable it and retain the previous setting. Every added parameter must be adjusted by a visible and reproducible improvement, not simply by a small numerical reduction in the residual. If the peak shapes still contain a systematic Lorentzian component, I can refine X and Y temporarily as a diagnostic test. I enable X and Y, rerun peak fit, and inspect the residual and the peak widths plot. In this example, the total Gaussian plus Lorentzian curve follows the measured peak width points more closely, and the residual decreases. This tells us that LaB6 pattern contains a measurable Lorentzian contribution. However, X and Y must be treated cautiously because they can include broadening associated with the standard itself, such as finite crystallite size or microstrain. Our aim is to create a transferable instrument baseline, not to store the complete physical history of this particular powder mount. Therefore, after recording the diagnostic result, I uncheck X and Y and set both values back to 0 before saving the profile. I do not rerun the global fit after this reset. I save the calibrated Gaussian instrument terms while excluding the suspected sample-related Lorentzian contribution. The profile is now ready to be saved. I verify that U, V, and W contain the refined values and that X and Y have been returned to 0. From the operation menu, I choose Save Profile. I use a descriptive file name that identifies the instrument configuration, radiation geometry, angular range, and reference material. For example, the name might include copper K-alpha break Brentano 20 to 70 degrees and LaB6. GSAS-II saves the results as an instrument parameter file with the .instprm extension. This file should be reused only for data collected with the same optical configuration, detector setting, slit arrangement, geometry, and alignment condition. Saving the file is not the end of the procedure. We must test whether it works independently. I start a new GSAS-II project and import the same LaB6 raw dataset again. This time, when GSAS-II asks for an instrument parameter file, I select the profile that was just created. Loading the file into a fresh project verifies that the calibration is genuinely reusable and is not merely retained inside the original project file. To validate the instrument profile with a structural model, I now import the LaB6 phase from the CIF file. I select the LaB6 structure, confirm the phase information, and link the phase to the imported powder histogram. The phase in histogram must be connected before a Rietveld or label refinement can be performed. I then apply the same working limits, approximately 20 to 70 degrees, and confirm that the background refinement option is enabled. I open instrument parameters and confirm that the saved U, V, and W values have been loaded correctly, while X and Y remain 0. In the background panel, the selected polynomial model and refinement plane are retained. I now choose Calculate and then Refine. GSAS-II asks me to save the validation project, so I save it as LaB6 test. The first agreement factors are only a starting point. We should not judge the instrument file from RW alone. The key evidence is whether the calculated peak positions and widths reproduce the LaB6 pattern without changing the calibrated U, V, and W terms. I now inspect representative peaks across the full angular range. The calculated peak centers should coincide with the measured reflections, and the calculated width should follow the observed profile at low, intermediate, and high angles. In this case, the peak positions are well reproduced, indicating that the saved instrument file is functioning as intended. I also examine the difference curve for repeated positive and negative peak-shaped residuals. Small local deviations are expected, but a systematic failure across all peaks should indicate that the profile, geometry, wavelength, or background model requires further attention. After confirming that the instrument profile works, the validation refinement can be improved in a controlled sequence. The background and histogram scale factor may be refined first. For break-Brentano data, sample displacement can be refined to account for the height of the specimen relative to the focusing circle. The unit cell parameter may be refined using the certified standard value as the starting reference. If additional sample-related broadening remains, it should be described with appropriate crystallite size or microstrain parameters rather than by immediately changing the instrument U, V, and W terms. The instrument parameter should remain fixed. During this validation stage, refinement quality should be assessed using the visual residual RWP, chi-squared, parameter uncertainties, and the Durbin-Watson statistic, while also checking that every refined value remains physically meaningful. This completes the procedure for generating and validating a GSAS-II instrument parameter file from LaB6 reference XRD data. The essential sequence is to define a reliable angular range, model the background, select clean peaks, refine intensities and positions in stages, diagnose individual widths, replace those widths with a smooth global profile, save the instrument-only terms, and finally test the file in a fresh project. A good instrument parameter file is not simply the one that gives the lowest residual for the reference pattern. It is the one that remains physically reasonable, transferable, and appropriate for samples measured under the same experimental configuration. Thank you for watching.